In our previous video, we were able to explain color and the observed color by electronic transitions between the HOMO and the LUMO. So we have said that an electron can go from the highest occupied molecular orbital to the lowest unoccupied molecular orbital, and if this energy required falls into the visible, which is mostly characteristic of transition metals and coordination compounds, that can be observed. Most of the electronic transitions fall into the ultraviolet, and what we're going to talk about here is that actually the energy levels that we can transfer from one to another does not necessarily have to be electronic levels. A molecule has many different kinds of energy levels. Let's say a molecule like oxygen has, of course, as you remember from the, so let me write the molecular orbitals. Yeah, sure, you can transfer electrons between different transfer electrons between molecular orbitals, but a molecule of oxygen also has vibration, and a vibration is also quantized, and a molecule of oxygen, like any other molecule, has also rotation, which is also quantized. This means that with electromagnetic light, or with light, we can transfer between energy levels of different kinds. So in here you see all of our electromagnetic spectrum. This small range is the visible range that the human eye is sensitive to. However, with other frequencies or wavelengths, we can excite other molecular levels of energy. For example, as we said, well, the valence electronic levels typically fall in the ultraviolet. If you're lucky enough, if the HOMO-LUMO difference is small enough, it will be visible. And this is the kind of spectroscopy that we call UV-vis, the ultraviolet visible spectroscopy. If you're actually exciting electrons from the core, say that this is your 2s, or it would be even more if this were the 1s, so all the way to here, the energy required falls into the X-ray. And a typical technique that does that is the CT scan and the X-ray techniques. It excites core inner electrons. Other types of spectroscopy is what we call infrared spectroscopy. As you all know, the more to the right you go, the lower the energy. So infrared can excite vibrational levels. That is, it can make vibrate molecules more or less. If you go more to the right, even less energy, the rotational levels. That's called microwave spectroscopy. And a microwave oven is exactly that. It excites the rotation of water specifically so that your food gets warm by rotating the water more and more. Okay? And in the radio waves, what you see is the nuclear spins, that is, depending on the number of protons and neutrons that you have, some of the nuclei have a net spin, and that will fall, the transitions among the different orientations of those little magnets will fall into the nuclear magnetic resonance, or also known as MRI. So there is a wide range of spectroscopies, a wide range of energies of photons that excite different energy levels of molecules. And that's something important to keep in mind, because what we call light is not necessarily the small range that the human eye is sensitive. Everything is light, and it actually interacts with matter at a different energy levels. Okay, so let's think about how we can represent the electronic transitions in a way that includes the other transitions. The curves that you see here, hopefully you're familiar, say that this is oxygen 2, okay? And you have, if you remember, so each oxygen is 2s2, 2p4, 2s2, 2p4, so I need to put 12 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That is following Hund's rule, the most stable configuration. That's what I call the ground state. And what you see here, this would be the R, the distance between oxygen and oxygen. And this is my minimum distance, the distance of the bond. Let's call it bond distance. Okay. Now, what happens if instead of pointing up, this points down? Well, this is not the most stable configuration, so this arrangement of electrons is called the excited state. So notice that you will have one of these curves, one of these electronic curves for each possible combination of electrons that you have. So you can represent an electronic transition that goes from the most stable, the ground state, to the first excited state. That would be, for example, this one, where the electron is pointing down. So this is one specific arrangement of electrons, this is another specific arrangement of electrons, and what you see here is that how the energy of that specific arrangement of electrons changes as a function of the distance. So if I were to separate oxygen from one another, the energy would go up. If you get them too close, the nuclei start repelling each other, the energy also goes up. And you can draw one of these electronic curves for each of the possible arrangements of the electrons in a molecular orbital diagram. Okay, so let's keep understanding how we can use these electronic curves. And so now for each of the electronic curves, since we said that each molecule has rotation and vibration, you can actually specify this would be the vibrational level number 1, this would be number 2, this would be number 3, and transitions among vibrational levels, this will fall into the infrared spectroscopy. And for each of the vibrational levels, there is rotational 1, rotational 2. So, and this is why you can see in these kind of diagrams how one can move from one energy level to another, in which includes both electronic, vibrational, and rotational. That's something that is actually very useful to explain fluorescence and phosphorescence, which is the topic of this next slide, because if we can pump a molecule from here to here, notice that we're not talking about electrons anymore because we are changing vibrational states and rotational states, but in any case, if a molecule can absorb all this energy, well, what happens to the energy up here? At some point, it would have to come down, wouldn't it? If you excite this molecule, at some point it will, the same way that a stone falls on the ground, a molecule should radiate the energy that has at some point absorbed. So that's the question. Why is that we talk about light being absorbed, but rarely about light being emitted? Where does this light go? And that's why we will use diagrams such as this one. This one is called Jablonski diagram. You don't have to remember this, but these kind of diagrams can explain phenomena like fluorescence and phosphorescence, or if you will, what's called non-radiative transitions. So let's think about that. Say that this is a molecule, this is my ground state, okay, and like any other molecule can absorb, most of the molecules will be at this distance, so they will absorb this energy, and they will end up in a highly vibrational, so that's highly vibrating molecule in my excited state. A different arrangement of electrons. Now, once the molecule is here, it can do different things. One thing that will do for sure is it will relax. It will relax vibrationally. In other words, it will come down from higher vibrational levels to lower vibrational levels. This, of course, will emits light, but this light falls in the infrared, so it's actually perceived as heat. Now, once it's here, if there is nothing else, it will make a big jump, and this jump is large enough to fall into the visible range, and that's when you have something called fluorescence. Notice that typically a fluorescent substance will absorb in this jump. This jump here is much larger, so it will fall in the ultraviolet range of the spectrum, and it will emit something that is closer to the visible. That's one possible pathway. The other pathway, and let me erase something. so that it doesn't get too clogged. The other pathway is that it relaxes in a non-radiative manner. We say non-radiative because it emits heat, but it emits actually infrared photons, and it jumps into another state that is forbidden, if you will, that it's not the first choice. It takes some time, it actually takes some time for these electrons or for these molecules to come down here, and because it takes some time, even after the initial radiation here, some molecules will still be in the excited state and slowly but surely will emit light. This is called phosphorescence. So the difference between fluorescence and phosphorescence is that fluorescence, the molecule comes down to the ground state almost immediately. For phosphorescence, it actually takes some time. So even after you stop the irradiating light, your substance will still be emitting some light, and all of them, as you notice, both fluorescence and phosphorescence will have a smaller energy because the jump is smaller than the initial one. Now, most of molecules do not possess fluorescence or phosphorescence properties. So what happens to most molecules' properties? Well, what happens is that there are other curves in here that allow each of the curves would come here, that allow what we call non-radiative transition, that is infrared. So when we talk about a substance absorbing light but not emitting any, that's not exactly true. Most substances, and you can every object, unless you are in a club right now, but I doubt it, every object that you see around is not emitting any light. It's not fluorescent, it's not phosphorescent. It's because it relaxes from excited states to lower state, just emitting infrared, also known as heat. Energy is conserved, but the way the molecules come down to the ground state is, if you will, less spectacular. It's just through heat. Actually, thanks to these non-radiative transitions, the heat that our planet is warm. That's the main role that the atmosphere has. It absorbs the ultraviolet and the visible light from the sun and radiates heat, and that keeps the planet at a warm temperature in which water is liquid and life can progress. And let me give you now a last example of what we've seen here, the Jablonski diagrams. And one of those is what you may have learned in your physiology courses, the retinal transition. So rhodopsin is a protein that exists in your retina, and this rhodopsin has a ligand that's called retinal, and this retinal has a bond that can be either in cis or in trans. Now, once the molecule, the retinal, is in trans, it emits a response to the brain, and it says, hey, there's some light in here. How is that possible? Well, your retinal is first excited by light, and it doesn't come down right away. There is some non-radiative transitions, and it ends up being here. This is what it's called a photo-induced reaction. It would take a lot of energy to go from here to here. However, through light, it jumps to the excited state, and the excited state, through non-radiative emissions, will end up in another valley, if you will, of rhodopsin that happens to be the trans. And when it's all trans, it will emit a response to the brain saying, I can see something, I can see light. As you can see, there are many applications of all these transitions, and all electronic transitions will always include some vibrational and some rotational. It's something to keep in mind because its range of applications is quite wide.